Thank you so much. Hi there, everybody. Yes, I'm Michael. I'm from Flare Lab at Oxford, and today I'll be presenting JaxLife, an open-ended agentic simulator written in Jax. So, in general, A-Life simulations, there have been quite a lot of them in the past. And overall, most of them aim to study life kind of on a computer, effectively how life can emerge, how intelligence can emerge, and effectively trying to study all of those types of questions, but in kind of a controlled computational way. In the past, there have been very many different simulations. So things like Tierra and Alvida, kind of looking at kind of programming languages, something like Linear, and then kind of more recently, something like Alien. All of these are very like useful, but to a large extent, many prior simulations focus on low-level elements. So, for instance, looking at the kind of chemistry or the physics of kind of structures, and then seeing how, for instance, life can emerge from those kind of low-level. Our simulation called JaxLife tries to take a different tack on this question. So what we focus on is instead only on high-level behaviors. So we kind of try and extract away all of the low-level things like physics and chemistry and try and only focus on high-level behaviors. The concrete design decisions that this leads to are, for instance, that our agents have fixed morphologies and they're effectively just points. And we don't really care about their kind of physical appearance. They are effectively just behaviors. These behaviors further are parameterized by neural networks, and these neural networks kind of learn and evolve via kind of a survival of the fittest type of approach. Another kind of addition that we add to our simulation is that agents can interact with Turing complete programmable computers slash robots, which enable them to do quite a lot of different things and kind of effectively make them able to change the world much more than if they were just on their own. And the kind of main idea behind JaxLife is effectively to start from a higher level of abstraction and see, what type of things like intelligence emergence can we study. So just a brief overview here of JaxLife. So as you can see, it's basically a 2D kind of top-down view of this big world. There's lots of little agents. Each of these red dots is an individual agent. And then there's kind of terrain. Terrain has many different properties. One of these properties is energy, and that is effectively just how much food basically is there in a particular cell. So, for instance, the green area here indicates a lot of food, whereas the brown area here indicates not an abundance or like a low amount. There's also other aspects, such as how efficiently an agent can move or kind of how costly it is to do any of its actions. Kind of as the blue kind of gets darker, that is where the agent kind of struggles to perform actions and it moves slower, whereas kind of on the green or on the brown, it moves more quickly. Then, as you can see here, agents can have control over the terrain. So by eating food, they can effectively reduce the amount of energy in a particular cell. And by planting food or effectively making the ground more fertile, they can increase the energy generated by that tile over the next few kind of iterations. Agents can also interact with each other, so they can steal basically energy from others, which is effectively kind of a predatory mechanism. And they can also gift energy, which can lead to kind of cooperative behavior. On the kind of this side, you can see that agents can also kind of interact and kind of control the motion of other agents. So, for instance, pushing them around, pulling them, or something like that. And then the final components in
JaxLife
are these little robots, which are indicated by these gray kind of circles. And robots are effectively also kind of entities in our system. They can perform the same kind of actions that agents can, but they're controlled in a different way, which we'll get to in a second. So let's just look at quickly how our agents are parameterized and kind of how they work. So what we have here is the agent observes basically a local area around it, and it observes both the entities, so the other agents and, for instance, robots that are close by, and it observes its own properties, things like how much energy it has, how old it is, stuff like that. And then it also observes a kind of local area of the terrain, indicating the properties such as how much energy there is, what's the movement cost, and so on. Each of these kind of different features are passed through kind of separate encoders. So the agents have a separate encoder to the robots, which in turn is also separate from the terrain. Each of these encoders effectively process these kind of input features into some sort of embedding. What we do then is we perform self-attention over these kind of entity embeddings and use cross-attention with the agent's own embedding to compute an effective kind of entity representation, indicating the important information of the entities around. Next up, the terrain effectively also goes through this encoder, and then we concatenate these two together to obtain a kind of world representation. This world representation is then input into a kind of recurrent network that outputs the action of the agent. You can see here that the kind of actions are relatively high level, so the agent kind of move around. It can eat, it can kind of push or pull, hit or feed or gift, for instance. It can kind of do asexual reproduction as one of its actions if it has enough energy. And then a few other features are that it can write a message or send a message to other agents, effectively communicating, and it can send a message to itself, effectively having a kind of notion of some kind of longer term memory in its own observations. And then finally, the agents can have control over the terrain by influencing the properties, i.e. making the kind of fertility higher or making the movement possible. Next up, let's look at robots. So robots have the same action space as agents, as I mentioned before, but they're controlled via a programming style interface as opposed to a neural network. So agents can basically program a robot by writing a message to its memory, and that controls how the robot kind of chooses its actions. And then one additional thing that robots can do that agents can't is that robots can read and write from the terrain, basically allowing them to act as kind of a longer term information storage unit for the agents. This is just an example of some of the instructions that kind of are included in this robotic programming language, but it's effectively a relatively kind of straightforward, or yeah, it's a relatively simple way of parameterizing their behavior. Now, the first question we wanted to answer is how practically useful are these bots for actual kind of agents? And to answer this, what we do is we basically develop visually useful and hand design behaviors and kind of see, is it possible given our parameterization features? One kind of example here is transportation. So you can see the bot here is kind of moving the agents around, and that allows agents to kind of traverse large distances without expending a lot of energy of their own. Here is a kind of example of communication. So where robots can transmit information across long distances without needing to actually physically move that distance, which can be quite efficient. And then here is kind of automated farming / terraforming type of notion, where robots can effectively increase the fertility or intuitively plant food over a large stretch of the map, effectively increasing the amount of energy available for agents without the agents themselves having to do that. So this is kind of more in a practical sense, just showing that robots can actually create useful behaviors. On a more theoretical kind of perspective, we actually show that these robots can comprise a Turing-complete kind of computation system, effectively allowing them in the infinite limit of, lots of robots and lots of space to compute any kind of computable algorithm. So how we show this is we basically reduce our system to rule 110. This is an elementary cellular automata where you basically have a 1D kind of line of bits that are either 1 or 0. And each of these permutations effectively have a different next state that that specific middle cell will turn into. And very similar to the game of life, you basically compute the next state for each row at the same time, or for each cell at the same time, and then place that down as the kind of next state of the simulation. So this, in short, is rule 110. And on the right here, you can see kind of a general animation of what that looks like. And on the left here, you can see that the robots in JaxLife can effectively implement this rule 110 and write those results to the terrain. So kind of in the infinite limit of having lots of robots and a lot of space, you can basically compute any computable function, which effectively says the complexity of our simulation is very high, and agents are capable of, or have the potential to do quite a lot of interesting and complex things. Now, just a little bit about how we kind of wrote this and how we wrote it and why. So we used Jax, which is basically a kind of recently released library that basically is a numerical library for kind of GPU computation. One reason that we use Jax is that it's very much faster than PyTorch. and it's kind of more easy to program kind of higher level behavior or like a simulation effectively in JAX, we found. It's also largely functional instead of kind of object-oriented as PyTorch is. And what that allows is that there could be significant optimizations by effectively compiling your kind of functional code and reusing that kind of very fast compiled code a lot of time. Yeah. Recently, in kind of reinforcement learning, there has been a trend of basically re-implementing environments in JAX. And the upshot of this has been that reinforcement learning kind of algorithms can train, hundreds or thousands of times faster than kind of prior methods, as you can see kind of on the figures here. So that's kind of the reason why you use JAX. And then another kind of beneficial reason is that using JAX, you can very easily scale across kind of multiple cores on a single GPU. And then using effectively the same code, you can scale across multiple GPUs quite effectively as well, which makes it much easier to kind of conduct scaling analyses and stuff like that. And then finally, there's no kind of CPU to GPU transfer, which is kind of commonly bottleneck in a lot of others. Now, just going on to some kind of qualitative results. Here is kind of an example of some simulation that's kind of halfway through completion. Or it doesn't really complete, but we just ran it for a fixed number of time steps, and this is roughly halfway through. And you can see there's definitely some kind of interesting behavior happening. So the agents on the left side here, you can see they basically move in this kind of diagonal line, whereas the robots on the right side here move in the opposite direction. We think there's quite a lot of pushing and kind of pulling happening here to increase the speed of these agents. And then you can see here the robots are effectively changing the terrain by virtue of this kind of darker blue line shown there. Some other results in terms of scaling. So at the top right here, we kind of investigate using the same starting conditions, but with different numbers of agents. And what we find is that we kind of see this very structured kind of line behavior only really when we exceed a certain number of agents. And with too few, that behavior doesn't really emerge. And then on the left here, you can see that we measure the amount of energy used across the whole simulation. And that's effectively a measure of how complex this civilization is based on how much energy all the agents collectively use. At the start of the simulation, you can see there's kind of relatively stagnant growth here. So not much is increasing. And agents are kind of just going around. Then kind of halfway through here, this corresponds to this kind of horizontal or diagonal lines. And there we can see this coincides with a big spike in energy usage. And then eventually, we think the agents exhaust the resources available, and then it kind of falls down again, and they kind of die out and actually don't use the agents anymore as much. Then just kind of quick conclusions/takeaways from this project. We hope that JaxLife could hopefully serve as kind of an interesting test bed to study these questions of intelligence, kind of how that emerges, and potentially if there are alternative routes to intelligence than what we as kind of humans effectively ended on. We can also kind of study tool use by basically looking at how these agents use their robots. And furthermore, we hope our simulation can enable kind of you're running the simulation with different features turned on and off to see, what the effect of those are on some properties that we are interested in studying. And then there's quite a lot of future work. So one interesting avenue would be to investigate different agent representations. So instead of encoding just a policy, encode something like an entire learning algorithm using a method such as VSML. Another idea is to evolve or kind of have some sort of reinforcement learning objective that agents learn to optimize during their lifetimes, as opposed to the only signal being kind of how many agents kind of reproduce. And then another kind of final point would be to obtain better metrics for quantitatively studying these behaviors kind of in a more grounded or kind of more numerical way. Thank you very much for listening. And this has been JaxLife, and I'm happy to answer any questions if you have.